Here is an example of RL circuit. So this RL circuit is in DC. That switch has been closed for a long time. So the switch has been closed for a long time, so there is some energy stored in the inductor. So remember one thing, as long as it's DC, inductor acts like a short circuit once it is fully energized. If there is no rate of change of current, there won't be any inductance in that coil. So at t equal to 0 minus, this is how the circuit is going to look like. 20 ohm, 20 ohm and 10 volt. Okay, now you can see 20 parallel with 20, that is 10 ohm. So I total equal to V over R total. So R total is 10 ohms, so 10 over 10, that is 1 ampere. I always write parallel combination like this, but you can say 20 times 20 divided by 20 plus 20. Okay, so the total current is 1 ampere. Out of 1 ampere, so these two resistors are equal, it's going to divide equally. But I can find by using current division rule. Current division rule, I1 equal to total current multiplied by opposite resistance over total resistance. Okay, that's 0.5 ampere. I1 equal to 0.5 ampere, and same way I2 equal to 0.5 ampere. By using KCL, I total must be equal to I1 plus I2. So that's the 0.5 is going across 5 ohms and going through 5 ohms, and 0.5 amperes going through R1 and 0.5 amperes going through R2. Now I can find the energy stored in the inductor. Just okay, energy U equal to half L I square. I know half L is 20, he gave us that as 10 millihenry. I square is 0.5 square. That value is 1.25 millijoule. That's the energy stored in the inductor. Now at t equal to 0, we open the switch. Okay, when you open the switch, immediately what happens? I total becomes 0. Okay, so I'm sure I can tell I total equal to 0 ampere. Now the property of inductor, it does not let the current change suddenly. That's the property of inductor. So just before opening the switch, there is 0.5 ampere current passing through this. So for sure I2 equal to 0.5 ampere, since inductor does not allow sudden change in current. Allow sudden change in current. Now how about I1? So this current has to have a closed path, so I1 is going to the same 0.5 is going to come over here. So I can say I1 equal to minus I2, which is minus 0.5 ampere. Okay. After a long time, if I say t equal to, long time is in the sense after 2 seconds or 3 seconds, that energy is going to be dissipated completely. But here the question he's asking about, find the time taken by the current I2 to reach 50% of its maximum value. So what is the maximum current here? So what happens if I draw it in graph format? So current initially through the inductor is 0.5. That 0.5 is going to come down like this exponentially. Okay, now the question he's asking about, what is the time taken right there? T equal to how much? Here he gave us this value as 50%, which is 0.25 ampere. This is I2. Okay, so So the equation for I2 equal to I2, which is initial current, times e to the power of minus t over tau. That's the current equation. Okay, current passing through that circuit. Now what is I2 initial current is 0.5 and 50% of the current. So the goal is we need to find this t equal to how much. This is what our goal. So tau is called time constant, time taken to reach the current to 32% of its initial value. Okay, so time constant, that value is L over R for RL circuit. That value is 10 milli divided by, what is the R total? From the inductor point of view, you have 20 ohms there. Okay, so which is 0.5 millisecond. That's the tau value. So I2 here is 0.25, because here he's asking about how much time it is going to take to reach the 50% of the maximum value, e to the power of minus t over 0.5 milli. Okay, so 0.25 divided by 0.5, which is 0.25 divided by 0.5, equal to e to the power of minus t over 0.5 milli. So this value is 0.5. Okay, 0.5. So if I bring to the other side, natural logarithm of 0.5 equal to minus t over 0.5 millisecond. So natural logarithm of 0.5 is minus 0.693 equal to minus t over 0.5 milli. Minus minus get cancel. So time t equal to 0.693 times 0.5 times 0.5 milli, that equal to 0.346 millisecond. Okay, as I mentioned, I mean, it's not going to take more than a second to discharge all of its energy across the inductor. Okay, thank you.